Hey folks, this is Captain Jones here to talk to you about how we could build something I'm going to call an automated calculator. So this is meant to be a bit of a stepping stone to kind of give you a little prelude into the rest of this course, and it's my attempt to sort of try to bridge the knowledge you have from EE360 and digital logic to this course to show you how we can take the circuits that you're already familiar with and start to combine those in ways that make something that, at least in this case, just kind of starts to look like a functional computer. We won't quite get there in this lesson, but hopefully they'll give you, enough of a big picture that that the rest of this course will make much more sense to you. So we've got two major objectives today. Number one is to start with just a little arithmetic circuit, one you have seen many times in EE360, and show you how we can take that. We can add some memory to it. We can add a counter, and that starts to give us temporary storage and even some automatic control over the arithmetic circuit, and that we can start to use that to do some fairly powerful things. Along the way, we'll actually get a little deep into how memory is built from flip-flops, because we'll have to build a couple of those little memory cells ourselves, and we'll see how those all come together. Okay, so let's get started. This is the automated calculator. I'm going to jump to Logicsim now and show you that I've made a little basic circuit here, and this little piece in the middle that I'm going to call my ALU, arithmetic logic unit, is just a simple adding subtracting circuit, same one we saw from EE360. So this piece in the middle here, this is my adder. As long as this mode bit is 0, then it's doing addition. 4 plus 4 in this case is 8. You may recall from EE360 that with the addition of these two components, I can effectively use the exclusive OR gate to toggle my B input, and by adding 1 to the carry in of my adder, I can effectively change this from A plus B to A plus negative B, which is the same as subtraction. So if I change this mode bit to a 1, instead of doing 4 plus 4, I'm now doing 4 minus 4, which is 0. So with this little circuit, I can do addition and subtraction. And we can see that here I got 4 and 4. If I add it together, it's 8. If I subtract it, it's 0. I can subtract 4 from 6, the result being 2. So this is just the arithmetic circuit that we saw last semester. It's decently useful on its own. Let's see if we can add some stuff to make it a little more useful. The first thing I might want to add is a little spot to store some memory, sort of like the little memory store button on your calculator. So all I'm doing is taking the output of my ALU and sending it to this device, which is a register, same register, style of register we saw last semester. So it's composed of 8 flip-flops to store 8 bits, and all I'm doing is my 8 bits of input is sort of ensuring that 1 bit each goes to the 8 flip-flops, and each of their outputs then are combined into my 8 bits of output. And the clock that's controlling my register goes to every flip-flop. The right enable line, which is controlling whether or not the flip-flops get an updated value from the input, goes to all of the devices. And so with this setup, I can I can store and read 8 bits at a time from my register. So if I'm doing with this 8 minus 4, the result being 4, I can store that by pressing this button. This is effectively tied to my right enable. And on the positive clock edge, then 4 gets stored in my register, and I can do all kinds of stuff over here, with my calculator, and that doesn't affect the value of my register because I'm not updating that. And okay, so I can store a value, which is I don't know, maybe that's useful if I'm doing a long calculation and I don't want to forget it. But one thing that might make this a little more useful is that to actually feed the output of that register back into the circuit. So what I can do here is change my B input slightly so that there's a multiplexer now that selects whether or not the second input to this ALU is the literal value, the 8 bits in B that I can select, or the output of this register here. So see, in this case, I'm performing. We'll change it to 0, so I'm getting the literal A and B inputs. I've got 4 plus 4. The result is 8. Let's do 12 plus 4. The result being 6 is 16. Store that in my register, So I've got 16, the value 16 here in my register, and now when I change this input line, this B select line, to a 1, I won't be, instead of getting the value 4 here, I'll be getting the value 16. So then 12 plus 16 is now 28. Okay, so this is getting more powerful now. What I can do is actually, I can enter two numbers directly as A and B if I want, perform some calculation on them, and then store that result, and then I can feed that result back into my calculator. So potentially now I can do start to kind of simulate things like multiplication or division, which I can sort of approximate as a series of additions or a series of subtractions. Okay, so this is getting a little more useful. Let's extend this idea. Let's say, one memory space is great, but I want a couple more. I want some more sort of memory space to use in my calculations. So we're going to expand this from one memory space to many. To do that, I want to sort of actually back up just a second, and we're going to start by just trying to store a single bit at a time. But we'll build a circuit that can store a single bit in any of 4 locations. So you can see here, I've got 4 flip-flops. Of course, each flip-flop can store a single bit. And so I've got 4 of them, and the hope is that I can start to create this memory arrangement where I can select which of these 4 locations I want to store my bit. So to do that, I'll need a clock signal, of course, going into my memory. I'll need a line for a single bit to denote the data that's coming into my memory, either 0 or 1. Those can go directly to each flip-flop, no problem. I'm also going to have my write enable line coming into my piece of memory. However, though that write enable line doesn't directly connect to each enable bit, on my flip-flops, because I don't, when I'm enabling one of these flip-flops, I don't necessarily want to enable all of them at the same time. I want to be able to select which of these flip-flops I'm enabling on any given clock cycle. And so, I've got 4 flip-flops, which means I need a minimum of 2 bits to select each one individually. So what I'm going to add to the circuit are 2 bits of address. This is a new input to this memory element. 2 bits to specify which of my 4 flip-flops I'm trying to talk to at any given point in time. And I'm going to send that address value into a decoder, which will set only one of these lines active that corresponds to the numerical value of the address. So right now address is 00. You can see in this picture. So the label M0 is the signal that's active because that's numerically 0. And so now what I can do is I can sort of control which flip-flop I'm trying to enable with these memory signals by ANDing them with my write enable. And so it's only if the correct memory line is active and if the write enable signal is active that a flip-flop is allowed to be enabled. And then I can use that memory line to also control which of these flip-flops are allowed to send data to the output by ANDing that memory line with the output of the flip-flop. So, so the output of this piece of memory, this RAM, is only going to be equivalent to whatever is the value in the flip-flop that is being addressed at a given point in time. So let's see this kind of in action. You can see here I got my I've got my memory cell here, 4 flip-flops with my decode logic, and so I'm addressing location 0, so you can see the M0 line is active. That means if I turn on my write enable, then it's just the enable line that goes to this first flip-flop that is sort of allowed to go high. I can change this address bit from a 0 to a 1, and now it's just the number 1 flip-flop that's allowed to be enabled. And it's if I go back to memory location 0, that's the only one whose output's allowed to go to my data out. I can change this to a 1, and the data being sent out from my RAM is whatever the value in memory location 0. If I change this to a 1, now the memory or the value being sent out is 0 because that's what's in memory location 1. Okay, so I can create a memory piece of memory that is 4 spaces tall and just 1 bit wide. I can use almost an identical circuit to expand this from 4 spaces to 16 spaces. And so I'm going to take a look at this circuit here. This is for my 16 by 1 RAM or 16 by 1 memory. And you'll notice the circuit looks extremely similar. The two differences are in my actual memory spaces, instead of my flip-flops, now I'm using my 4 by 1 memory instead of just those individual flip-flops. So I've got 4 spaces that can store 4 spaces each, which gives me 16 memory spaces. And the second big change is that my address bits have to expand. So in order to address 16 spaces, I need 4 bits of address. So I've got 4 address bits. The 2 most significant bits go to my decoder and select which of these sort of 4 by 1 RAM circuits are being selected. And it's the lower 2 bits of this address that are sent to each of these memory cells to select within each one the correct memory space. And so we can see, if my data is at a 1, I toggle my clock. Okay, then memory location 0 should have been stored a 1, which it looks like it is. If I jump in here, I can see that actually it is also. The memory location 0 has that 1 value. I can change my address to a 1, meaning I'm selecting a slightly different address to be read, and the value there is a 0. Memory is more or less it's formed just in this way. I'm sort of, I'm applying the same circuit over and over and over again to create larger and larger pieces of memory. If you're curious, you can see how I would take this 16 by 1 piece of memory to form a 64 or even a 256 by 1 piece of RAM, the 2 circuits at the bottom. But for the purposes of this circuit, we'll say 16 spaces. That's plenty for me to do some kind of neat mathematical stuff. And instead now I want to sort of expand it to be able to store more bits at a time. You can imagine that going from 4 to 1 to 16 by 1, we sort of were making our memory taller. We were giving it more spaces to address. And but since my calculator works, operates on 8 bits of data at a time, I want to be able to store 8 bits at once. So in this case, in that sense, I want to expand my memory horizontally. So to do that, I follow the same tactic that I used before, just to make my 8 bits register, which is literally I'm going to place these memory locations side by side. So this is now my 16 by 8 memory cell. And to compose that, all I did was take my 16 by 1 pieces of memory and stack 8 of them, place 8 of them horizontally right next to each other. And so when my 8 bits of data come into my memory, each bit goes to its own 16 by 1 memory cell. The address controls where in each of these 16 by 1 memory cells those bits are being stored, and then I can read out those bits also on the output to my RAM. Okay, so in place of now this was my sort of 1 8-bit register, I can put my 16 by 8 RAM, and now I can do some much cooler things. So here I've got 15 minus 4, the result being 11. Actually, let's reset this really quick. Okay, so let's say I've got 4 plus 4, the value is 8. I'm going to store that in address 0, so I'm going to press my store button, and on the positive clock cycle, now I get this value 8 in memory location 0. If I go to memory location 1, nothing's there because I haven't stored anything yet. So let's do something a little more fun. Let's say I've got, would this be 14 minus 4 is 10. I can store that in memory location 1. And in memory location 0 is still the value 8 that I stored there, from a previous calculation. And I can use my bselect to choose if that's the value that I want to go into my ALU. And okay, so I get 16 spaces now where I can store temporary values, and that's really useful, to be able to do start to do some more complex calculations. I can kind of, I can evaluate a polynomial function sort of one term at a time, or do, more complicated logarithmic functions or exponential functions maybe by, using those memory spaces. So we're gonna make one more major change to this circuit, but I'm gonna do one change just prior to that to sort of help set us up. So, excuse me. So the one kind of minor change I'm going to make is to move what was up here, the A register, down below the ALU and call it my accumulator. So this is just going to sort of make the final step that we take here in just a minute a little bit easier for us. And So with this change, you know, the biggest difference is that really that my calculations, they take a little bit longer to set up. Whereas previously, if I wanted to do 11, let's see, 11 minus 4, or sorry, 15 minus 4, I could do that, you know, sort of in one go. I can put 11 on A, put 4 on B, tell the ALU to subtract. Since I don't have that A register to play around with, what I need to do is do this in sort of 2 steps. So what I need to do is I'll first set B to a 15, and I'll store that value in my accumulator. Then I'll change B to a 4 and perform my subtraction and store the result of that in my accumulator. And the result of that is 11. So something like addition or subtraction just takes, you know, sort of like one little extra step. But this is going to make our lives just a little bit easier. Because the last thing that I want to do is take this, you know, this arithmetic circuit, which I can do some neat calculations with, and start to automate it.